Hello and welcome. I'm Alexander Bird. I'm the Peter Sowerby Professor of Philosophy and Medicine at King's College London, where I teach in the Department of Philosophy and in the GKT School of Medical Education. I'm also Director of the Philosophy and Medicine project at King's, which is funded, like my chair, by the Peter Sowerby Foundation. Epidemiological models have been frequently mentioned in the media lately. What are they, and how do they work? In this talk, I will give you some answers to those questions. I will today focus on one model in particular. This is the model, for example, used by Sunetra Gupta and her colleagues at Oxford, and it is, I believe, one of the models influencing the government's thinking about the spread of COVID-19 and the SARS-CoV-2 virus that causes it. This is the model that was developed by Kermack and McKendrick in 1927, and has its origins in the work of Sir Ronald Ross, who won a Nobel Prize for his research on the transmission of malaria. The epidemiological model we will look at is the SIR model. SIR stands for Susceptible, Infectious, Recovered. It aims to give us an understanding of the relationship between the number of people infected with the disease and the numbers who are uninfected and still susceptible, and those who have recovered and are no longer susceptible. So the total population is divided into these three groups, or compartments as they are called, and we want to know how fast people move between them, from susceptible to infectious, and from infectious to recovered, over the course of an epidemic. This may allow us to predict the course of the epidemic, or to intervene to slow it down, or even prevent it. So this graph here gives an idea of how a typical epidemic might progress according to this model. We can see that our model makes certain assumptions. It assumes that the overall population stays constant, there are not people being born and, more relevantly perhaps, dying. For current purposes, that doesn't matter, since over the course of a few months, the number of births and deaths is not very large compared to the overall population. Another assumption is that the infected people and the infectious people are the same. Again, that isn't always true, because there can be a latent period after becoming infected, but before being infectious to others. For current purposes, it's okay to assume that there isn't a significant latent period. Let us call susceptible people susceptibles, and the number of them we will call S. Let us call the infected and infectious people the infectives, and the number of them is I. And the number of recovered people, the recovereds, is R. So the total population is N, where N is S plus I plus R. So everyone is either susceptible or infected or recovered. We start by asking how many of those who are susceptible will become infected in one day. Think of a single infected person who comes into contact with N other people in a day in a way that could potentially infect them. And now think of the chance that one such encounter will lead to a new infection. We use the Greek letter Tor for the probability that an encounter between an infectious person and a susceptible leads to the latter becoming infected. So if all the N people are susceptible, the number of people being infected in a day by our single infective is Tor times N. This is an important number, the number of people an average infected person will infect if everyone else is susceptible. And usually we use the Greek symbol beta to denote it. So for example, if Tor is 0.25, meaning that any encounter has a probability of a quarter of leading to a new infection, and N is 8, meaning that the infectious individual encounters 8 other susceptible people, then there will be 2 new infections that day, so beta equals 2. It's intuitively obvious why diseases spread quickly in cities such as London and New York, where many people use crowded public transport to commute to work. A Londoner or a New Yorker will come into physical proximity with a large number of people, meaning a high N. And Tor may be high also because those encounters may have a higher chance of passing on the disease. Think of people rubbing shoulder to shoulder on a crowded tube or subway train. Let's think a little bit more about Tor, N, and beta. Tor is partly a biological matter, how contagious the disease is. But it will also depend on social factors. In some societies, people engage in a greater degree of physical contact when they meet. In some circumstances, there will be better opportunities for personal hygiene. These factors will make a difference to the value of Tor in those societies. N is the average number of encounters a person has of a kind that would allow for the transmission of the disease. Thinking about the current measures to combat the spread of COVID-19, hand washing and wearing masks work to reduce Tor, while the lockdown and isolation reduce N. That said, the idea that Tor and N are entirely distinct is somewhat doubtful. Consider the social distancing practice of not coming within 2 meters of other people. On the face of it, that reduces N. If 2 meters were some kind of hard boundary, so that beyond 2 meters the disease cannot be passed on, but within 2 meters it might be, then keeping people beyond 2 meters is a way of reducing the number of encounters that might spread the disease. On the other hand, and more realistically, the 2 meter rule doesn't operate quite like that, since there can be transmission beyond 2 meters. This social distancing measure can then be thought of as a way of reducing the chance of transmission, in which case this measure looks more like as a reduction in Tor, the chance of transmission. For this reason, while Tor and N are useful in setting up the model, it's better on the whole to focus on beta, the number of new infections that an infectious individual would bring about each day when everyone else is susceptible. So we want to know the number of new infections in the population as a whole. We said that each infective infects beta susceptibles each day, and there are I infectives in the population, so the number of new infections is beta times I. That's on the assumption that everyone an infective meets is susceptible, which will be true or close to the truth early on in an epidemic. However, in the middle of an epidemic, not all the people an infective meets will be susceptible. Some will be immune because they have recovered. Let us return to our single infective for a moment. They encounter N people each day. Some of those will be susceptible, but not all. What proportion will be susceptible? We take that proportion to be the same as the proportion of susceptible people in the population as a whole, which is S divided by N. So if 50% of the population are already immune, then in our example, although our infective encounters 8 people, only 4 of them are susceptible, and so given that Tor is 1/4, there will be only 1 person newly infected each day. That means, in what we have already said, we must replace little n by little n times S over big N, and so beta must be replaced by beta times S over big N. So, the daily number of new infections is beta IS over big N. The new infections all come from the susceptible proportion of the population. So we can say the daily change in the number of susceptibles is minus beta IS over N. The minus sign is there to show that the change in susceptibles is a decrease. Each day, beta times IS over N people become infected and so are no longer among the susceptibles. Each day, some of those who are infected recover. We use another Greek letter, nu, to denote that proportion. So, the daily change in the number of recovereds is nu times I. Nu is the proportion of infected people who recover each day. One way to understand nu is to see that it is related to the duration of the illness. If it takes 4 days from being infected to recovering, then we would find that each day 1/4 of those infected would recover. So nu is inversely related to the duration of the disease, D. Nu equals 1 over D. This diagram represents the duration of a 10-day illness. The final square with a tinge of green is the day on which this person recovers. Imagine many people with this illness. We can see that on any given day, that 1/10 of the people will recover. The duration D is going to depend primarily on the biological nature of the illness. It will also depend on the medical care available. Are there drugs that will help cure the illness? On the other hand, some treatments that help with symptoms in fact increase the duration of an illness. Fever-reducing medicines can extend the time to recovery because fever is one of the body's mechanisms for combating infection. We can work out the value of D and so of nu by looking at the medical records of infected people. How does the number of infectives change? That's the number of susceptibles who have become infected minus the number of infectives who have recovered. A very brief interlude now for those who like their mathematics. Mathematicians will express changes using what we call derivatives. So the rate of change of the number of susceptibles over time is expressed by ds by dt. And so we can write our equations 1 to 3 like this, which is the set of differential equations at the heart of the SIR model. It's not mathematically straightforward to solve these equations analytically since they are non-linear, but we can use them nonetheless to show how exactly S, I, and R change over time depending on the values of beta and nu. Let's look at the equation telling us how the number of infectives changes. If this number is positive, then the number of infective people is increasing and the epidemic is growing. More people are becoming infected than are recovering. The epidemic will be on the wane when this number is negative, when there are more people recovering than are becoming infected. That's to say when beta is over n is less than nu I, which we can simplify by dividing by I and rearranging s, n, and nu to give us beta over nu is less than n over s. This number, beta over nu, is very important in epidemiology. As we can see, it is key to telling whether an epidemic is waning or is growing. It tells us how rapidly a new epidemic will grow. It can also describe the successive efforts to contain an epidemic. It can be used to tell us how many people need to be immune in order for there to be herd immunity, as we will see shortly. Epidemiologists call this the basic reproduction number, or the basic reproductive number. It's given the symbol R0. I'm using here a curly R to distinguish it from the R for recovereds, but sometimes a normal R is used. So this equation, R0 equals beta over nu, defines R0. In a moment we will look at an equivalent and alternative definition of R0. We can say therefore that the epidemic is waning when R0 is less than n over s. This I call the waning rule for epidemics. A more intuitive route to grasping what R0 means requires remembering that nu is equal to 1 over d, where d is the duration of the infectious period. So we can also define R0 like this. R0 is beta times d. Remember that beta is the number of new infections brought about each day by a single infective, assuming that everyone else is susceptible. D is how many days they are infectious for. So beta times d is the total number of new infections the infective brings about before recovering and losing infectiousness. So for example, let beta be 2/3. So each day our single infective infects, on average, 2/3 of a person, so to speak. And imagine that they are infectious for 3 days. By the end of their infectious period, they will have infected 2 people. So this is a good way to understand R0. It's the number of new infections brought about, on average, by a single infective before they recover. At this point, it's important to distinguish discussion of an epidemic early on, when the number of infectives and recovereds is small compared to the total population, all of whom are susceptible, from the discussion of an epidemic later on, when a substantial number of people have been infected and have recovered or possibly have died. Very often, we are interested in the features of an epidemic in its early phase when we wish to know what to expect and how to combat the spread of a disease. In the early days or weeks of an epidemic, even if the number of infectives and recovereds is in the thousands, it remains the case that in a country where the total population numbers in the tens of millions, almost everyone is susceptible. So S can be regarded as very close to N, and so N over S approximates closely to 1. Therefore, early in the epidemic, we can say that the total number of infections is decreasing and the epidemic is waning when R0 is less than 1. If, on the other hand, R0 is greater than 1, the epidemic is continuing to spread. Therefore, we can also write the reigning rule as beta times D is less than 1. Consider the infected person who infects beta people in a day. He is infectious for D days, and therefore he infects overall, on average, beta times D people. At the end of D days, he is no longer infectious but has recovered. So that is one fewer person infected. If he has infected more than one person by that time to compensate for his own recovery, then the epidemic will grow. If on average he has managed to infect less than one person, then the epidemic is on the wane. Yet another way to grasp the same point is to think about the average interval between causing infections, called the serial interval. If an infected person on average takes a time t to bring about a new infection, and if t is less than d, the duration of their illness, then the infected person, on average, will be able to bring about a new infection before they recover and cease being infectious. On the other hand, if t is greater than d, then on average, an infected person will have recovered before they can infect someone else. We can relate t to things that we have already seen. T is the reciprocal or inverse of beta. If someone infects 2 people per day, then on average, that is half a day between infections. If someone infects 4 people per day, then that's the same as 6 hours between infections. The break-even point is when t equals d. Let's say 1 over beta equals d, which is the same as beta times d equals 1, and so R0 equals 1. The serial interval for COVID-19 is thought to be around 4 days. We can see why epidemiologists focus their attention on R0. It's much the same thing as focusing one's attention on beta, but the idea that a key question is whether R0 is greater or less than 1 is attractive and easy to grasp. Measles has a very high R0, over 12, indicating that it is one of the most infectious of diseases. Smallpox has a lower R0 at less than 6. The basic reproduction, R0 for COVID-19, is thought to be between 2 and 3. This is roughly in the same range as the 1918 flu pandemic, and is more than the seasonal flu, whose R0 is between 1 and 2. It isn't possible to be precise about R0 because it varies from place to place, both for the social reasons that I've mentioned already, and also because the biology of a disease may be affected by climate. Avian flu H7N9, which appeared in several outbreaks among humans in China in 2013 and in subsequent years, is roughly 10 times more deadly than COVID-19. But because its R0 amongst humans is less than 1, it was never able to cause an epidemic. The repeated outbreaks were caused by its continued presence amongst poultry, which forms a so-called reservoir for the virus. We have seen that if R0 is greater than 1, the disease will spread in the population. Let's return to our case where beta, the number of new infections caused by a single infective in each day, is 2/3, and d, the duration of the infectious period, is 3 days. We saw that R0 is therefore 2. This means that our individual patient, between becoming infected and his recovery 3 days later, has infected 2 other people, So we have doubled the number of infectious individuals. After a further 3 days, these 2 individuals have recovered, but in the meantime, they have each infected 2 further people, meaning that after 6 days, there are 4 infected individuals. Likewise, after 9 days, there are 8 infectives, after 12 days, there are 16 infectives, and so on. After 1 month, there will be 1,024 infectives, and after 2 months, there will be over 1 million infectives. This is the exponential growth of infectives that one sees in the early phase of an epidemic. Let us think about a real case, measles. Measles has a basic reproduction number of between 12 and 18. Let's work with the more conservative 12. Measles has a very high R0 because the chance, Tor, that a susceptible person will get measles after being exposed to an infectious person is very high, about 90%. A measles patient is infectious for about 20 days. If their infectiousness were the same throughout that period, then after 2 months, a single infection in a susceptible population would lead to almost 2,000 cases and about 2 to 5 deaths. After another month, there would be over 70,000 cases, which would typically mean between 70 and 200 deaths. The estimate of the number of cases of measles spreading in a susceptible population that I've just given may well be an underestimate in certain respects. That's because measles is most infectious in the early prodromal phase, when symptoms are just beginning to occur. The simplification of our model doesn't take this into account as it stands. If we were to treat the duration of the infectious period as just being a week, while R0 is still 12, then after 2 months there would, in principle, be 430 million infected individuals. Now clearly that's unrealistic. We can only use R0 to tell us directly how many new infections there will be when almost everyone an infectious person encounters is susceptible. But if the disease spreads unchecked, then in due course more and more people will have had the disease and will have recovered. These people will make up a larger and larger proportion of the population that any infected person meets. And as a result, it will become more difficult for an infected person to infect many others, and eventually they will not be able to infect anyone else before they have recovered themselves. So, in this circumstance, the epidemic will die out, even though there are still some susceptible individuals left in the population. This is the state of herd immunity. So let's recall the waning rule for epidemics in general, that is to say, the waning rule for epidemics, including epidemics not in their early stages. So that's R0 is less than N over S. As the epidemic continues, the number of susceptibles, S, will get smaller, and so N over S will get larger, and must eventually be larger than R0. The waning rule is therefore very helpful in telling us what proportion of the population needs to be immune in order for herd immunity to arise. That's particularly useful in deciding what proportion of the population needs to be vaccinated in order for there to be herd immunity. Herd immunity is important because not just everyone can be vaccinated. Many babies and young children are simply too young to be vaccinated, and some individuals are allergic to some vaccines. These people need to be protected by herd immunity. Vaccination is a means of becoming immune without having been infected with the disease. That makes no difference to the use of the model. We can treat them just like recovereds. Let's take all the non-susceptibles to be immune. That's both the recovereds and the infectives. If immunity is brought about by vaccination, then there shouldn't be many infectives, if any, so we can treat the whole population as either susceptible or immune. The proportion of people who are immune is therefore N minus S over N, which is the same as 1 minus S over N. So we can rewrite the waning rule as follows. S over N is less than 1 over R0, which is the same as 1 minus S over n is greater than 1 minus 1 over R naught. The left-hand side is the proportion of the population that is immune, as we just saw, and the right-hand side is equal to R naught minus 1 over R naught. So we can rewrite the waning rule as saying that there is herd immunity when the proportion of the population that is immune is greater than R naught minus 1 over R naught. This value, R naught minus 1 over R naught, is often referred to as the threshold for herd immunity, and it's expressed as a percentage. Herd immunity, in simple terms, occurs when a sufficiently large proportion of the population are immune that it is unlikely that any infected person will encounter and pass on their infection to any remaining susceptibles. More precisely, that probability is low enough that on average an infected person will have recovered before they pass on the disease to someone else. The susceptibles are therefore protected by the immunes. We can look at a real example. We saw that R naught for measles is between 12 and 18. Let's start by assuming that it is 12. In that case, the threshold for herd immunity is 12 minus 1 over 12, which is 92%. If R naught is 18, then the threshold for herd immunity is 18 minus 1 over 18, which is 94%. Given such a high threshold for herd immunity, a sustained and vigorous program of vaccination is needed to maintain it. If one did not employ a vaccination, could herd immunity to measles be achieved naturally? For that to happen, over 90% of the population would have to have had measles. And since measles has a fatality rate of between 1 and 3 per thousand, that would imply tens of thousands of deaths. Furthermore, about a quarter of cases require hospitalization, which would be a huge burden on the health services. Furthermore, even if herd immunity were to be achieved, it would only be temporary, as a new generation is born who are susceptible but not immune. The latter will eventually reduce the proportion who are immune below the threshold, allowing the disease to take hold again if introduced from outside the population, or if there are pockets of the disease in the population from which it has not entirely disappeared. COVID-19 is rather less infectious than measles. R naught for COVID-19 is between 2 and 3. If it's 2.5, then for herd immunity, about 60% of the population would need to be immune, either by vaccination or by having contracted the disease. Could herd immunity be achieved without a vaccine? Well, that's something I might discuss in another video, but for now we can calculate the number of deaths that this would imply if the vulnerable are not given special protection but were just as likely to be infected as anyone else. The 60% herd immunity threshold means that in the UK, with a population of 67 million, 40 million would have to be infected. The proportion of the infected who die, the infection fatality rate, is thought to be about 0.66%. So the number of deaths would be over 260,000. Earlier, I emphasised that the SIR model makes a number of assumptions. That means that the model, as it stands, is limited in its applicability to those cases where the assumptions are true or near enough to the truth. I'll briefly mention a couple of such assumptions and limitations, although there are others that we could discuss. The model makes the assumption of homogeneous mixing. This is the idea that the susceptibles, infectives, and recovereds are found in the same proportions throughout the population. That's clearly not going to be entirely true. There may be geographical differences, and there may be other differences amongst social groups in the way that their members interact with each other or with other people. These differences mean that the homogeneity assumption doesn't hold. The failure of the homogeneous mixing assumption can lead to an overestimate of the future size of an epidemic. At the same time, it might mean that although we have reached the herd immunity threshold on average across the country, there are places where, or groups among whom, the threshold has not been reached, making an outbreak possible. I earlier mentioned that one assumption we make is that everyone who contracts the disease will recover, whereas we know that many cases can be fatal in some diseases, such as COVID-19. The model can be used to predict mortality when we know what proportion of the infectives will die rather than recover. For most diseases, that's not a limitation on the model, since the deaths are not large in proportion to the total population or even in relation to the recovereds. With the policies currently in place, it is thought that the current COVID-19 outbreak will cause in the region of 20,000 deaths in the UK, quite possibly rather more, and so millions worldwide. These are terrible numbers which will bring with them a great deal of human misery. But as a proportion of the population, that is less than 1 in 3,000, which isn't big enough to make a difference to the functioning of the model. On the other hand, if we were modelling the Black Death, then this would not be an assumption that we could reasonably make. The SIR model does make another assumption that is more relevant. It assumes that those who recover stay in the recovered category, but we know that immunity can sometimes be lost, in which case people will become susceptible again. If that's the case, then we will have to make a significant modification to the SIR model. We have to make it an SIRS, Susceptible, Infectious, Recovered, Susceptible model, which will have consequences for the mathematical operation of the model. We do not yet know the degree to which this applies to COVID-19. There are other ways in which the model might be modified in order to account for different types of disease. If the opportunity arises, I will look at these and at other ways of modelling epidemics in a future video. I also plan to say more about how all this bears on the current coronavirus crisis. How does the strategy of the UK government relate to this model? Is herd immunity part of that strategy? Or should it be? Or should it not be? Can we end the epidemic or return to anything like normality without a vaccine? Visit philosophyandmedicine.org for more videos soon. You will also find there the text upon which this talk is based, as well as the slides. Thank you for watching.